Right now, as you read this, there are 2,000 thunderstorms crackling across Earth. Lightning is striking somewhere 100 times every second. Hurricane-force winds are spinning in massive circles hundreds of miles wide, and above your head, invisible rivers of air are racing at 200 miles per hour, steering entire weather systems across continents. All of this, every raindrop, every snowflake, every gust of wind, follows laws so precise, so elegant, that once you understand them, you'll never look at the sky the same way again. Welcome to the Veda Cozy Scientist. Tonight, we're unlocking the secrets of weather, the science behind every storm, rainbow, and rumble in the sky. And here's my gentle warning. This might be just interesting enough to keep you awake. But if you find yourself wide-eyed at 2 a.m. thinking about cumulonimbus clouds and the Coriolis effect, at least you'll be smarter for it. So close your eyes if you like, let your shoulders drop, and take a long, slow breath. Let's explore how weather actually works. The invisible ocean. We live at the bottom of an invisible ocean, a vast sea of gases we call the atmosphere. Unlike the ocean of water, we don't need a snorkel, though it can occasionally make your hair do strange things and send papers flying. The atmosphere is surprisingly thin, proportionally about as thick as the skin on an apple. Most of it hugs Earth in a tight, shallow band. If you've flown at 35,000 feet, you've already risen above a good chunk of it. The layers of our sky. The atmosphere is made of distinct layers, each with its own personality. The troposphere is where we live and where all weather happens. It stretches about 7 miles high, taller near the equator, shorter near the poles. This is where clouds form, rain falls, and wind gets up to mischief. Above that lies the stratosphere, home to the ozone layer, Earth's natural sunglasses shielding us from harmful solar rays. Higher still is the mesosphere, where meteors burn up in bright streaks. The thermosphere hosts auroras and satellites, where temperatures can reach thousands of degrees, yet wouldn't feel hot because the air is too thin to conduct heat. At the very edge, the exosphere merges with space itself. But let's stay in the troposphere, our home layer. The air here is 78% nitrogen, 21% oxygen, with the rest a cocktail of trace gases including carbon dioxide and water vapor. The heartbeat of weather, here's where things get fascinating. Air is a fluid, just like water. It flows, swirls, tumbles, and crucially, it reacts to temperature and pressure changes. Warm air rises because it's less dense. Cold air sinks because it's heavier. This simple principle, warm up, cool down, is the heartbeat of all weather. The sun doesn't heat Earth evenly. The equator gets intense sunlight while the poles get very little. Land warms faster than water. Mountains are colder than valleys. These differences create pockets of warm and cold air, and because nature loves balance, the atmosphere constantly tries to even things out. Picture a sunny patch of ground. As the sun warms it, the air above begins to rise. As it rises, it cools. Cooler air can't hold as much moisture, so water vapor condenses into tiny droplets, forming clouds. Meanwhile, surrounding cooler air rushes in to replace the rising air. This movement is called convection, the same principle that cooks a roast or moves bubbles through boiling soup, just on a planetary scale. Pressure. The invisible force air has weight. At sea level, atmospheric pressure is about 14 pounds per square inch, like having a small cat gently pressing on every inch of your body. High-pressure systems are calm and stable, bringing clear skies. Air is gently sinking, which discourages cloud formation. Low-pressure systems are lively. Air is rising, encouraging clouds and often leading to rain or storms. The difference in pressure between areas creates wind. Air moves from high to low pressure, attempting to balance things out. Atmospheric tidying, though with much more mess involved. The Coriolis effect. Earth's twist because Earth spins at over 1,000 miles per hour at the equator, moving air gets twisted. This is the Coriolis effect, and it means winds curve as they travel to the right in the northern hemisphere, to the left in the southern hemisphere. This elegant scientific quirk shapes everything from gentle breezes to massive hurricanes. It's physics doing its thing, creating the swirling patterns we see from space. The atmosphere is always shifting, always flowing, never the same from one moment to the next. Even on a calm day, there are quiet currents slipping past you, subtle changes in humidity, invisible dances of temperature. This swirling engine runs without switches or commands. It's self-organizing, driven by physics and the golden rule of thermodynamics. Energy spreads out. Heat moves from hot to cold. Pressure equalizes. Water evaporates, falls, and evaporates again. And that's why we have weather. Earth is a restless sphere wrapped in gases, dancing with sunlight and spinning through space. Every gust, every cloud, every raindrop is part of this continuous quest for equilibrium. The sun's orchestration. The sun sits 93 million miles away, yet it's the ultimate puppeteer of our planet's weather. Without it, Earth would be a cold, dark rock with no wind, no clouds. The sun's energy arrives as electromagnetic radiation, warming Earth's surface. Here's the twist. The sun doesn't heat the atmosphere directly. Instead, it heats the ground and oceans, which then radiate warmth upward, like a stovetop heating the air above it. Uneven heating creates motion. Not all parts of Earth absorb sunlight equally. The equator receives direct sunlight, while the poles get a dimmer glow. This creates a persistent imbalance. Tropics warm up while polar regions stay chilled. When there's imbalance, nature tries to smooth things out. The result? Constant, beautiful atmospheric motion. Warm air near the equator rises, creating low pressure at the surface. Air from higher pressure regions flows in. Meanwhile, the rising air travels aloft toward the poles, cooling as it goes. At higher latitudes, it descends and starts moving back toward the equator. This large-scale circulation forms convection cells. We've identified 3 main cells in each hemisphere: Hadley cell, nearest the equator; Ferrel cell, mid-latitudes; polar cell, near the poles. Together, these cells redistribute heat from equator to poles, keeping the atmosphere circulating like a giant, invisible conveyor belt. Global wind patterns within these cells live major wind systems. Trade winds blow east to west near the equator. Reliable winds that sailors have used for centuries to cross oceans and sometimes accidentally discover new continents. Westerlies blow west to east in mid-latitudes, pushing weather systems across North America and Europe. Polar easterlies blow east to west near the Arctic and Antarctic, bringing frigid air toward mid-latitudes. These winds would travel straight lines if Earth weren't rotating. But the Coriolis effect nudges moving air off course. This deflection is why cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The jet stream rivers in the sky high above us flow jet streams, narrow bands of fast-moving air snaking along boundaries between major air masses. The most famous is the polar jet stream, flowing between cold polar air and warmer mid-latitude air at 9 miles altitude, reaching speeds over 200 miles per hour. Jet streams form where strong temperature contrasts exist. They steer weather systems across continents like invisible highways. When a jet stream dips or rises, it can bring cold snaps or heat waves, influence storm development, and make weather forecasters either very happy or extremely nervous. They also affect flights. Ever noticed westbound flights take longer than eastbound? You've caught a ride on the jet stream, the atmospheric equivalent of a moving sidewalk, only much faster. Earth's tilt. The gift of seasons Earth is tilted 23.5 degrees. This tilt gives us seasons. As Earth orbits the Sun over a year, different parts receive different amounts of sunlight. When the northern hemisphere tilts toward the Sun, it experiences summer, longer days, higher sun, more concentrated energy. Meanwhile, the southern hemisphere experiences winter. 6 months later, the roles reverse. This shifting sunlight pattern changes temperature distributions globally, affecting wind patterns, storm tracks, and oscillation. Oceans. The thermal batteries oceans covering 70% of Earth's surface aren't passive players. They absorb huge amounts of solar energy and store it like thermal batteries. Water heats and cools more slowly than land, which is why coastal regions have milder climates. Oceans also move. Giant currents like the Gulf Stream transport warm water across great distances, helping regulate climate. When ocean conditions shift during El Niño or La Niña events, they have global ripple effects on rainfall, droughts, and temperatures. So without ever leaving your cozy spot, you floated through Earth's weather engine. The sun heats unevenly, causing air to rise and fall. The spinning Earth deflects this air into graceful curves. Jet streams carry it like high-speed ribbons, and our planet's tilt ensures nothing stays the same for long. The result? A planet where no 2 days are truly alike, where every breeze and rain pattern are part of a grand planetary ballet, powered by sunlight and shaped by motion. Moisture in the water dance, moisture in the air is easy to overlook until it's fogging your glasses or making your hair misbehave. But invisible water drifting through the atmosphere is central to shaping weather. It creates clouds, causes rain and snow, fuels storms, and produces some of the sky's most beautiful scenes. Understanding humidity, humidity is just a fancy word for water vapor in the air. Water vapor is water in gas form, and air can hold more or less depending on temperature. Warm air holds more water vapor, cold air holds less. This is why summer feels muggy, while winter air feels crisp and dry. Absolute humidity is the actual amount of water vapor present, like 12 grams per cubic meter. Relative humidity is more emotional. It's a percentage comparing how much water vapor is in the air to how much the air could hold at that temperature. At 100% relative humidity, the air is saturated and condensation begins. That's when you see dew, fog, or clouds forming. High humidity makes hot days feel worse because sweat doesn't evaporate easily. Your body's natural cooling system struggles. In dry air, sweat evaporates quickly, making you feel cooler, though possibly like a desert lizard. How clouds are born. Clouds look soft and fluffy, but they're made of countless tiny water droplets or ice crystals. It takes about 1 million droplets to make a single raindrop. Despite their delicate appearance, an average cumulus cloud can weigh hundreds of thousands of pounds, as heavy as a jumbo jet, just floating as if gravity took the day off. Here's how clouds form. Evaporation. The sun heats water from oceans, lakes, rivers, and soil, turning it into water vapor, rising air. Vapor rises because warm air is less dense. Cooling. As air rises, pressure drops, air expands and cools. Condensation. Cooler air can't hold as much vapor, so excess vapor condenses into tiny droplets, or ice crystals. These droplets cling to microscopic particles, dust, salt, pollen, called cloud condensation nuclei. Different cloud types form depending on how air rises. Stratus clouds. Gentle rising creates flat gray layers. Very unstable, moist conditions create towering giants that power thunderstorms, cirrus clouds. High-altitude wisps made of ice crystals, often signaling weather changes. Lenticular clouds form over mountains, looking like flying saucers. From clouds to precipitation. Clouds don't automatically produce rain. Droplets must grow large enough to overcome air resistance. This happens through coalescence, droplets bumping together and merging. When they reach about 2 mm in diameter, they fall as raindrops. Interestingly, raindrops aren't teardrop-shaped despite what cartoons suggest. They're shaped like hamburger buns, flattened on the bottom by air resistance. Two large drops split into smaller ones as they fall. Snow's geometric beauty. When temperatures stay below freezing from cloud to ground, you get snow. Snowflakes form when water vapor freezes directly into ice crystals. Their shape depends on temperature and humidity. Needles, plates, or classic six-armed stars form under specific conditions. The molecular structure of water, H2O, causes molecules to bond at specific angles, creating symmetrical hexagonal patterns. Under a microscope, snowflakes reveal breathtaking geometric details sculpted by temperature and moisture alone. While no two snowflakes are exactly alike, probability-wise, given quintillions of flakes over winter, some must be pretty similar. Other frozen precipitation sleet. Snow partially melts, passing through warm air, then refreezes into ice pellets before hitting the ground. Freezing rain. Snow melts completely into rain but falls through shallow cold air near the surface, staying liquid, supercooled, until hitting surfaces and instantly freezing into dangerous ice. Hail forms in strong thunderstorm updrafts. Ice pellets get tossed up and down, collecting frozen layers like an onion. They can range from pea-sized to grapefruit-sized, thankfully rare. Dew and frost. Sometimes water doesn't fall from the sky but condenses on surfaces. Dew forms when ground cools overnight, allowing moisture to condense on grass and leaves. If temperatures drop below freezing, dew becomes frost, decorating surfaces with intricate ice patterns. The water cycle, all this moisture movement, evaporation, condensation, precipitation, is part of the water cycle, nature's endless recycling program. Water evaporates, rises, forms clouds, falls as rain or snow, flows into rivers and seas, and starts over. This cycle has run for billions of years and is essential to every form of life. Weather fronts air doesn't need to be still for clouds to form. Fronts, boundaries between different air masses, often trigger dramatic weather changes. When warm, moist air meets cold, dry air, the warm air is forced upward, triggering condensation and rain. That's why many weather changes begin with passing fronts. Next time you see a cloud, know it's more than a floating puff. It's the visible tip of an invisible process, a delicate balancing act of temperature, moisture, and motion. Every droplet, every wisp, every shower is part of a vast, elegant water dance happening above our heads. Thunderstorms, the sky's fireworks. When the atmosphere throws a party, they rumble, flash, pour, and sometimes toss hail at your roof. Yet they're simply products of air, water, and electrical flare. How thunderstorms form. At the heart of every thunderstorm is warm, moist air rising into cooler air. An updraft. This usually starts from surface heating on hot summer afternoons. As warm air rises and cools, it reaches its dew point, the temperature where water vapor condenses. This releases latent heat, giving air another boost upward like strapping rockets to a balloon. A cloud begins growing. With enough moisture and instability, it becomes a towering cumulonimbus, a vertical beast stretching up to 10 miles high, higher than Mount Everest. Inside, chaos brews. The updraft shoves warm, moist air higher, while gravity pulls cooled air and precipitation down in a downdraft. This up and down motion drives the storm's engine. 3 stages of thunderstorms. Cumulus stage. Warm air rises, forming a cloud, like blowing up a balloon. Mature stage. The cloud grows vertically, raindrops form, lightning begins, thunder debuts. Updrafts and downdrafts coexist in a swirling dance. Dissipating stage. The downdraft dominates, rain cools the surface, cutting off warm air supply. The storm collapses and fades. Lightning. Nature's electrical balance. Lightning is nature's way of balancing electrical charges with spectacular flair. As storms churn, ice crystals and water droplets bump together and become electrically charged. Lighter ice particles gain positive charges and rise to the cloud top. Heavier hail and water drops become negatively charged and sink to the bottom. This charge separation creates enormous voltage differences, millions of volts. Eventually, air can't resist anymore, and discharge occurs. The process begins with a step leader, a faint path of charged particles zigzagging downward. When it nears the ground, the electric field intensifies, and the ground sends up a streamer to meet it. When they connect, a powerful current surges through, creating brilliant lightning. The lightning channel heats to around 50,000 degrees Fahrenheit in microseconds, 5 times hotter than the sun's surface. This sudden heating explosively expands air, creating a shockwave we hear as thunder. Light travels faster than sound, so you always see lightning before hearing thunder. To estimate distance, count seconds between flash and rumble, then divide by 5 for miles. 10 seconds equals about 2 miles away. Types of lightning cloud to ground. Most dramatic and dangerous intracloud. Leaps between separate clouds, ball lightning, glowing orbs, still somewhat mysterious, sprites and blue jets. High altitude phenomena shooting upward into the mesosphere. Looking like red jellyfish, a single lightning bolt carries over 1 billion joules of energy, enough to power a small town briefly. It can cause wildfires, damage buildings, and be deadly. When thunder roars, go indoors. Hail and wind hail forms in strong updrafts. Water droplets get carried high, freeze, fall, get lifted again, and collect more frozen layers. Each loop adds a layer, like rolling a snowball. Eventually, hailstones become too heavy and fall, ranging from pea-sized to softball-sized. Thunderstorms also produce strong winds as downdrafts push air toward the ground, spreading out rapidly in downbursts. Very destructive, sometimes mistaken for tornadoes. Supercells and tornadoes. Some thunderstorms spawn tornadoes. These special storms are supercells with a rotating updraft called a mesocyclone. This rotation comes from wind shear, changes in wind speed/direction with height, creating horizontal spinning that gets tilted vertically by strong updraft, gust fronts, and storm chains. The gust front is the leading edge of cool air pushed out by a storm's downdraft. As it spreads, it lifts warm air ahead, potentially creating new storm cells, a weather-based game of tag. The constant dance at any moment, roughly 2,000 thunderstorms are happening on Earth. They're reminders of how dynamic our atmosphere is, brief but powerful expressions of nature's energy, temporary disturbances in the atmosphere's endless quest for balance. When the sky lights up with lightning and follows with deep rolling thunder, it's not just noise, it's the sound of the sky releasing tension, one electric exhale at a time. Nature's giants, tornadoes and hurricanes. When the atmosphere really makes a statement, it unleashes its most dramatic spectacles, tornadoes and hurricanes. These mighty tempests are headline acts in Earth's meteorological theater, swirling masses of raw energy that can reshape landscapes and rewrite coastlines. Tornadoes. Spinning columns of fury. Tornadoes are rotating columns of air stretching from thunderstorm base to ground. They're short-lived, often just minutes, but astonishingly intense, holding records for the strongest surface winds ever measured, over 300 miles per hour, faster than formula. Formation ingredients. Strong thunderstorm, usually a supercell, rotating updraft, mesocyclone, wind shear creating horizontal rolling motion. Thunderstorm updraft tilts rotation vertically. Rotation tightens and stretches downward. If the funnel touches ground, the process is delicate, depending on subtle changes in pressure, moisture, and terrain. Some storms flirt with formation for hours without producing one. Others drop twisters with little warning. The enhanced Fujita scale tornadoes are ranked EF0 to EF5 based on damage. EF0 breaks branches, knocks over signs. EF1, EF2 moderate to considerable damage. EF3 severe damage. EF4 devastating damage. EF5 tears homes from foundations. Total devastation. Most tornadoes are weak. EF0, EF1, but occasionally monsters emerge capable of flattening neighborhoods and throwing cars like paperweights. Tornado Alley tornadoes are most common in the central U.S. Plains, Tornado Alley, Texas through Oklahoma, Kansas, Nebraska, and South Dakota. Geography here is perfect. Warm, moist air from the Gulf of Mexico meets cold, dry air from the Rockies and Canada under wide open skies. But tornadoes occur everywhere except Antarctica. Waterspouts form over water. Even the UK sees several yearly, though they're mild and rather polite. Hurricanes, massive rotating storm systems hurricanes, also called cyclones or typhoons depending on location, are massive rotating systems forming over warm ocean waters. They can be hundreds of miles wide and last days or weeks. Formation requirements: warm ocean water, at least 79 degrees Fahrenheit, extending 150 feet deep, pre-existing atmospheric disturbance, thunderstorm cluster, low vertical wind shear. Varying winds would rip developing storms apart. When these align, warm water evaporates, adding moisture to air. As moist air rises, it cools and condenses, forming clouds and releasing latent heat. This heat warms surrounding air, causing more rising. As air spirals inward due to the Coriolis effect, a low-pressure center forms. A tropical depression is born. With continued intensification and organization, it becomes a tropical storm. When sustained winds reach 74 miles per hour, it's officially a hurricane. Hurricane anatomy: I. Calm, clear, low-pressure center with light winds and possibly blue sky. Eye wall. Ring of towering thunderstorms containing strongest winds and heaviest rain. The most dangerous part: rain bands, spiraling bands of showers, extending outward for hundreds of miles. Saffir-Simpson, hurricane wind scale, categories 1, 5 based on sustained wind speeds. Category 1, 7.4, 9.5 Morehouse, roof/tree/power line damage. Category 5, 157 plus Morehouse, catastrophic destruction, areas uninhabitable for weeks/months. Beyond wind, storm surge, sea level rise from storm winds pushing water toward shore is often the deadliest aspect, especially in low-lying coastal areas. Combined with heavy rain, 2+ feet over days, it causes widespread flooding far inland. Warmer ocean temperatures provide more energy, but the total number of storms hasn't increased dramatically. Instead, we're seeing more intense storms, more Category 4, 5 hurricanes holding more moisture, meaning more rainfall at landfall. Climate's heat redistributors. Interestingly, hurricanes serve an important function. They help redistribute heat from tropics toward poles, moving excess thermal energy away from the equator. In a strange way, they're part of the atmosphere's endless quest for balance. Unlike tornadoes, hurricanes are easier to track and predict via satellites and computer models, allowing several days' warning for preparation and evacuation. The cycle completes once hurricanes move over cooler water or land. They weaken. Cut off from warm water fuel, the storm's engine sputters, winds die, rains taper off. What remains is days of cleanup. But meteorologically, the storm has completed its dramatic arc. Despite their power, both tornadoes and hurricanes express the same fundamental principles governing all weather. They're symptoms of imbalance: heat needing to move, pressure seeking equilibrium. They're not freak events, but entirely natural outcomes of forces keeping Earth's atmosphere alive and in motion. Next time you see swirling clouds from space, remember, these are Earth's most powerful stories written in air and water. Turbulent, sometimes terrifying, but also astonishingly beautiful, reminders of just how alive our sky really is. Wind, the invisible sculptor of our world. You can't see it, but you feel it dancing through your hair, pushing leaves across sidewalks, occasionally flipping umbrellas inside out. It's gentle and wild, playful and destructive. Yet it's really just air that refuses to sit still. The simple truth at its most basic, wind is caused by differences in air pressure. When one region has higher pressure than another, air moves from high to low to balance things out. The greater the pressure difference, the stronger the wind, nature's version of tidying up. The results aren't always tidy. Think of pressure differences like hills and valleys. Air flows downhill from high to low just as water would. But unlike water, air doesn't move in straight lines thanks to Earth's rotation. The Coriolis effect gently nudges moving air, deflecting it right in the northern hemisphere, left in the southern hemisphere. This gives wind its characteristic curves and shapes global patterns. Global wind belts near the equator, intense surface heating creates rising warm air and low pressure. Air spreads poleward aloft, sinks around 30 degrees north and south latitude, creating high pressure, then flows back toward the equator as trade winds, steady east to west winds sailors depended on for ocean crossings. Between 60 degrees latitude, winds blow west to east as westerlies, responsible for most weather systems moving across North America and Europe. Near the poles, polar easterlies flow from east again, bringing frigid Arctic and Antarctic air toward mid-latitudes. This is Earth's global circulation system, breaking the planet into wind belts and jet streams. Local winds, small-scale drama. Some of the most fascinating winds occur locally, shaped by mountains, valleys, and coastlines.
Sea breezes.
On sunny days, land heats faster than water. Warm air above land rises, creating low pressure. Cooler ocean air rushes in to replace it. A gentle sea-to-land breeze. At night, the process reverses as land cools faster than sea. Mountain winds. During the day, air near slopes heats and rises, drawing cooler valley air upward. Anabatic wind. At night, air cools and becomes denser, flowing back down into valleys. Katabatic wind. Famous regional winds: Mistral, southern France. Cold, dry wind blowing down the Rhone Valley toward the Mediterranean, sometimes exceeding 50 miles per hour, shaping regional climate and architecture. Santa Ana winds. California. Hot, dry desert winds blowing toward the coast, exacerbating wildfires. Chinook winds. Rocky Mountains. Dry air descending from mountains onto plains, causing temperatures to rise 40 degrees Fahrenheit in under an hour, like nature's giant hairdryer, earning the nickname Snow Eater. Sudden and sneaky winds. Microbursts. Powerful downdrafts from thunderstorms, descending rapidly and spreading out on the ground, causing damage mimicking tornadoes and posing serious aircraft hazards. Dust devils, mini whirlwinds forming on hot, dry days from uneven ground heating, usually harmless, spinning columns of air and debris a few feet wide and dozens of feet high. Gales and cyclones, large-scale wind systems with intense low pressure. Gales have sustained winds over 39 miles per hour, strong enough to bend trees. Cyclones bring hurricane-force winds, torrential rain, and massive storm surges. Jet streams. High-altitude rivers. These fast-moving ribbons of air at the tropopause travel 100, 200 mph, flowing west to east and meandering like lazy sky rivers. They form where sharp temperature contrasts exist, like boundaries between cold polar air and warmer mid-latitude air. Jet streams shift north and south with seasons. Their strength and position influence everything from storm tracks to droughts. When they dip or wobble unusually, they can trap weather systems in place, leading to extended heat waves, heavy rain, or prolonged cold snaps. Winds shaping power despite being invisible, wind shapes our world profoundly. It transports moisture, spreads seeds, carries pollen, and erodes rock into sand over time. It sculpts sand dunes in deserts and snow drifts in the Arctic. It powers sailboats and turbines, generating electricity without burning fuel. Wind also plays crucial roles in temperature regulation, carrying warm air from hot places and cool air to warm ones. On hot days, breezes feel like lifelines. On cold ones, they bite through coats. Wind chill measures how cold it feels when wind removes heat from skin. It doesn't lower temperature, but certainly feels like it. Freezing rain. Snow melts completely into rain, passing through warm air, but then enters wind as language. While wind may seem chaotic, it follows precise laws of physics, governed by pressure gradients influenced by topography, temperature, and Earth's rotation. Whether gentle rustling or howling storms, wind is a language the planet speaks every day. Next time you hear trees swaying or feel a breeze graze your cheek, appreciate the silent, swirling presence of wind. It's a constant companion, always moving, always reshaping air around us. Though we can't see it, wind is one of the clearest signs that the atmosphere is alive, in motion, and full of quiet power. Winter's icky armistry. When winter arrives, it transforms the world. Trees stand bare, ponds freeze like polished glass, and air bites at your nose. Snow drapes rooftops, softens sound, and paints landscapes in hushed white. But behind this peaceful picture lies fascinating science. Snowflakes, frozen geometry. A snowflake begins as a tiny dust particle high in the atmosphere. Water vapor condenses directly onto this speck and freezes, forming an ice crystal. As it floats through the cloud, more vapor condenses and freezes onto it, causing growth. The shape depends on temperature and humidity, which constantly change as the flake falls. That's why no two snowflakes are exactly alike, probability-wise. Most form classic six-armed hexagonal shapes due to water's molecular structure. Each H2O molecule bonds at specific angles, forming symmetrical repeating patterns. Some flakes look like plates, others like needles or stars. Under microscopes, they reveal breathtaking geometric detail, all sculpted by temperature and moisture alone. Snow is light but adds up fast. A cubic foot of fresh, fluffy snow weighs 5 pounds depending on moisture content. Wet snow is denser and heavier than dry powder. Sleet, freezing rain, and frost sleet. Snowflakes partially melt, passing through warm air, then refreeze into ice pellets before hitting the ground, bouncing and creating crunchy, slippery layers. Shallow, cold air near the surface. Rain doesn't refreeze while falling, it's supercooled, but freezes instantly upon hitting surfaces, creating dangerous ice glazes that make roads treacherous and snap power lines. Frost forms on cold surfaces during calm, clear nights when surface temperature drops below the dew point and freezing. Water vapor skips the liquid phase, depositing directly as solid ice crystals on grass, windows, and windshields, with delicate feathery shapes. Hoar frost forms under very specific conditions: clear skies, calm winds, moist atmosphere, growing complex structures like needles or ferns, creating fairy tale effects across landscapes. Ice fog occurs when tiny supercooled water droplets freeze into minuscule ice crystals near the ground in extremely cold places, below -20 degrees Fahrenheit, creating dense frozen mist common in Alaska and northern Canada. Wind chill, cold weather, feels colder than thermometers say thanks to wind chill, a real measure of how quickly wind strips heat from your body. Your skin naturally warms the thin air layer around it. Wind blows this away, forcing your body to work harder to stay warm. For example, at 20 degrees Fahrenheit with 15 miles per hour wind, it might feel like 5 degrees Fahrenheit. Wind chill doesn't change actual temperature, but affects how quickly frostbite or hypothermia set in. Blizzards and snow squalls blizzards aren't defined just by snowfall, but by wind and visibility. Sustained winds/gusts of at least 35 miles per hour, with visibility reduced to 1/4 mile or less, lasting at least 3 hours. You could technically have blizzards without new snow if loose snow blows around. Blizzards can paralyze cities and cause whiteout conditions, making short trips incredibly dangerous. Snow squalls, brief but intense bursts of snow and wind appearing suddenly, reducing visibility in seconds. They're short-lived, under an hour, but cause sudden temperature drops and hazardous driving. Winter's importance. Winter weather is crucial. Snowpack in mountains provides essential fresh water when melting in spring. Ice helps regulate Earth's temperature by reflecting sunlight. Even frost and snow help insulate soil, protecting plant roots from extreme cold. Next time you see your breath or catch a snowflake on your glove, remember you're witnessing one of the atmosphere's most complex performances. Each icy detail, from frost-tipped leaves to snow-covered fields, is the product of precise, elegant physics. Fog and atmospheric whispers. Some weather creeps in quietly. No thunder, lightning, or dramatic snow. Just gentle thickening of air, a soft gray curtain blurring the world and muting morning. This is fog, the most mysterious of weather's children. What is fog? Fog is nothing more than a cloud at ground level. It forms when water vapor condenses into tiny liquid droplets suspended near the surface. These droplets are so small they don't fall as rain. Instead, they float, scattering light and limiting visibility, making the world feel closer and quieter. Types of fog: radiation fog. Forms on calm, clear nights when the ground cools rapidly. As ground loses heat, it chills air above it. If air is moist and temperature drops to the dew point, condensation occurs and fog settles. Common in valleys or low-lying areas where cool air collects, usually appearing early morning before sunrise. Radiation fog is delicate. Light breezes stirred away as morning sun warms the ground, air heats, and fog slowly evaporates, like a curtain being drawn back. Advection fog forms from air masses moving across surfaces of different temperatures. Warm, moist air blowing over cold surfaces, like sea breezes over chilly coastlines, cools to the dew point, forming fog. Can blanket large areas all day if cooling continues. Common along coastlines. Upslope fog, found in hilly/dimensions terrain when moist air is forced to rise up slopes. As air climbs higher, it cools due to lower pressure. If it cools enough to reach dew point, fog forms. Can occur day or night and lingers until wind patterns shift. Evaporation fog. Steam fog forms when cold air moves over warmer water. Warm water evaporates into cold air just above it, increasing humidity. Sudden mix of warm moisture and cool air causes immediate condensation, forming wisps rising and curling like steam. Beautiful sight above lakes, rivers, or hot tubs on chilly mornings. Freezing fog occurs when air temperature is below freezing, but fog droplets remain liquid, supercooled. When droplets contact surfaces, branches, car mirrors, wires, they freeze instantly, creating rime ice, a rough, milky white layer. Unlike frost, which forms directly from vapor, rime forms from liquid droplets freezing on contact, sometimes building up quickly. Mist, similar to fog but less dense. By definition, if you can see more than 1 kilometer, about 0.6 miles, it's mist. Below that, it's fog. Mist feels lighter, more suggestion than event, but built from the same tiny droplets. Haze. looks similar from a distance but caused by dry particles, dust, smoke, pollution, rather than water droplets. Scatters light differently, giving skies dull, washed-out appearance. Doesn't feel damp like fog. Fog's effects on senses. Fog affects sound interestingly. In dense fog, sound waves scatter and get muffled, making noises seem closer or farther than they are. A train horn might sound distant one moment, startlingly close the next. This adds to fog's mysterious feel, blurring not just vision but all senses. Fog also tricks with light. Headlights hitting dense fog reflect off water droplets, bouncing back at the source and creating glare. Why driving in fog is difficult, and high beams are almost useless. Fog lights mounted lower aim under the densest fog, improving visibility. Cultural weight. Fog has cultural and emotional significance, appearing in poetry, film, mystery novels, and bedtime stories. It can feel peaceful or ominous, romantic or eerie. It's a setting, mood, and metaphor all in one, inviting you to pause, listen, and look more closely. Behind all that softness is solid science: dew points, condensation, temperature gradients, and air movement. Fog may seem like nature's quietest weather, but it has rich, active life. Next time you wake to fog-wrapped world, step outside and feel dampness on your skin. Remember, you're standing inside a cloud built not in the sky but at your feet. Weather at its most intimate, wrapping around you like a gentle secret suspended between air and water, between visibility and imagination. Heat, drought, and silent challenges. Sometimes weather doesn't arrive with drama. No thunder, lightning, or swirling snow. Instead, it creeps in slowly, turning up temperature degree by degree until everything feels heavy, sluggish, and too still. Heat waves, prolonged extremes. Heat waves are prolonged periods of unusually hot weather. At least 3 days with temperatures well above average for that location and time of year, often combined with high humidity. What counts as extreme heat? Las Vegas. But heat waves can last a week, 2 weeks, or even longer, especially when reinforced by stagnant high-pressure systems. Causes at the heart of most heat waves is a high-pressure system, ridge on weather maps, acting like a giant atmospheric lid. Air under high pressure sinks, and as it sinks, it warms. Descending air also suppresses cloud formation, allowing more sunlight to reach the surface. With no clouds for shade and no rising air for rain, land bakes day after day. In urban areas, urban heat islands amplify heat waves. Concrete, asphalt, and human activity absorb more heat during the day and release it slowly at night, keeping temperatures elevated. Cities can feel uncomfortably warm at night, while countryside nearby cools off. Trees, grass, and open soil release heat more efficiently, while city blocks hold it like thermal sponges. Humidity's role. When air is humid, your body struggles to cool through sweating. Sweat is natural air conditioning. It evaporates from skin, taking heat with it. But if air is already saturated with moisture, sweat evaporates slowly, making you feel hotter than actual temperature. This is where heat index comes in, like wind chill in winter, measuring how hot it feels when humidity is factored in. For example, 95 degrees Fahrenheit with 55% humidity might feel like 110 degrees Fahrenheit. Prolonged extreme heat isn't just uncomfortable, it's dangerous. Heat exhaustion and heat stroke are serious health risks, especially for older adults, children, and those with pre-existing conditions. Symptoms include dizziness, rapid heartbeat, nausea, and confusion. Major heat waves see spikes in emergency calls and hospital visits. Cooling centers, shaded parks, and well-timed fans can be life-saving. Droughts, silent and creeping. While heat waves are loud and immediate, droughts are silent and creeping. A drought is prolonged below average rainfall, leading to water shortages. It doesn't announce itself. It simply begins when rain stops showing up. Droughts can last weeks, months, or years. Some build slowly, others arrive suddenly after dry winters or failed rainy seasons. Effects depend on location but are far-reaching. Shrinking rivers, cracked soil, dried reservoirs, stressed crops. In extreme cases, droughts lead to famine, forest die-offs, and migration. Types of drought: meteorological drought affects soil moisture and crop health. Hydrological drought, low water levels in rivers, lakes, and aquifers. Socioeconomic drought, water shortages affect economy and society. Restrictions, irrigation failures, rising food prices causes several factors cause. Atmospheric circulation patterns, El Niño/LCRN Niño, disrupting normal rainfall. Persistent high-pressure systems, changes in ocean temperatures, long-term climate shifts. Drought is closely linked to rising global temperatures. As temperatures increase, evaporation rates rise. Water disappears faster from soil, lakes, and vegetation. Even when rainfall occurs, it might not offset evaporation losses. Intense rain following drought often doesn't help much. It runs off hardened soil, unable to soak in, sometimes causing flash flooding. The circular relationship: heat waves and droughts are often circular. Drought dries land, reducing evaporation, allowing temperatures to climb higher. With no moisture to absorb sun's energy, more heat goes into warming air and ground, a feedback loop locking regions into long spells of dry, sweltering weather. Adaptation and beauty: despite challenges, both are natural parts of Earth's climate system, occurring for millions of years. But in recent decades, frequency and intensity have increased in many parts of the world, attributed partly to climate change. Adaptation is becoming crucial. Cities invest in green roofs and tree canopies, farmers switch to drought-resistant crops and smarter irrigation, and water conservation becomes part of everyday life. Parched landscapes reveal patterns in cracked earth, wind-blown grasses, and defiant trees standing under harsh skies. Heat waves turn sunsets into fiery masterpieces. And when rain finally returns after long drought, it's not just weather, it's a homecoming. Next time air is still and heat settles in, take a slow breath. You're witnessing weather's quieter side, not flashing or rumbling, but reshaping things in silence. Heat and dryness may not make headlines like storms, but their effects run deep, carved into soil, memory, and the atmosphere's endless balancing act. Optical wonders: the sky as artist. Some weather phenomena enchant rather than overwhelm. They appear in quiet aftermath of storms, or when sunlight meets moisture just right. These are gentle wonders of the atmosphere, optical illusions and subtle spectacles reminding us the sky is, at heart, an artist. Rainbows. Light's colorful dance. A rainbow isn't an object you can touch. It's an optical phenomenon. When sunlight passes through raindrops, it gets bent, refracted, reflected off the drop's back, then bent again, exiting. This bending and bouncing splits light into component colors: red, orange, yellow, green, blue, indigo, violet. Each color bends slightly differently. Red least, violet most. The result is a circle of color. We usually only see a semicircle because the ground blocks the rest. Unless you're viewing from airplanes or high mountains, you might glimpse the full circle hanging in midair. Primary rainbow angle is always about 42 degrees from the direction opposite the sun. The sun must be behind you and rain/mist in front. You can never reach rainbows. They move with you. You're not seeing the same rainbow as someone nearby. Each viewer sees a slightly different version, built from light entering their eyes alone, as personal as fingerprints made of light. Double rainbows. A second fainter arc outside the first occurs when light reflects twice inside raindrops before exiting. The secondary rainbow appears higher, with reverse colors: red bottom, violet top. Between the two arcs is often a darker band called Alexander's band. Halos, sundogs, and light pillars when sunlight interacts with ice crystals, not raindrops. In high-altitude clouds, different optical wonders emerge. Halos, bright circles, often with subtle rainbow edges, forming around sun or moon when light passes through hexagonal ice crystals bending light at 22 degrees, results in ghostly rings floating around the sun like celestial crowns. Common in cold weather when upper atmosphere is rich with ice. Sundogs, parhelia, bright spots appearing on either side of the sun, often within halos, look like small, colorful sun duplicates, especially vivid when sun is low, caused by ice crystals oriented just right like tiny floating mirrors. Light pillars, vertical beams of light appearing to shoot straight up from sun or street lamps, caused by flat plate-like ice crystals slowly falling through air and reflecting light in columns. Look otherworldly but require no aliens, just calm atmosphere and right ice. Glories and coronas glories. Despite grand names, they're delicate and subtle. Series of colored rings forming around your head's shadow when cast onto clouds or fog banks. Most often seen from airplanes when aircraft casts shadow on clouds below, surrounded by shimmering color rings, created by backscattered sunlight interacting with tiny droplets. Pilots call it glory of the pilot. Coronas form when light diffracts around individual water droplets, creating tight, colorful rings around sun or moon. Unlike halos, coronas are small and close to bright objects, often seen through thin clouds, selective pearlescent appearance. Crepuscular rays, also called God rays, beams of sunlight appearing to radiate from the sun, often during sunrise/sunset when sun is low and clouds scatter light. Rays seem to fan across sky, but it's perspective at work, like railroad tracks appearing to converge in distance, caused by light streaming through gaps in clouds or mountains, illuminating particles in air, dust, moisture, pollen. Light and shadow create sharp contrasts our eyes interpret as rays. Green flash, rare event occurring just before sunrise or after sunset when sun is almost entirely below horizon. For a second or two, the sun's top edge can appear green. This happens because atmosphere acts like a prism bending sunlight. Blue and green light bend more than red and orange. Under right conditions, last sunlight sliver may appear green. Brief blink and you'll miss it. But sailors and sky watchers have cherished sightings for centuries. Moonbows, lunar rainbows. Moonbows are exactly what they sound like. Rainbows formed by moonlight instead of sunlight. Much fainter because moonlight is weaker. You need just right conditions. Full, nearly full moon. Rain/mist in air. Moon positioned low behind you. Moonbows often appear white or silver, but if you look closely or photograph with long exposure, you might spot pale colors. Nature's gallery, all these phenomena remind us light and atmosphere constantly play together. We don't always notice the show, but when conditions are right, the sky becomes a canvas for optical marvels, subtle or bold, fleeting or lasting. You don't need fancy equipment, just curiosity, willingness to look up, and sometimes patience to wait for perfect combinations of light, moisture, and timing. Whether rainbows arching after summer storms, halos encircling wintry suns, or faint glories floating around airplane shadows, each is a quiet whisper from the sky, reminding us nature doesn't only work in thunder and lightning. It also speaks in color, shimmer, and light, bending gently through air and water. Weather may shape the world, but light paints it. And every now and then, the atmosphere becomes not just a system, but a gallery. Geolocal weather variations. Weather can be intensely local. Sunshine for you while your friend miles away shelters from rain. But it's also wonderfully global. Around the world, weather varies wildly depending on geography, latitude, ocean currents, and elevation. Monsoons, seasonal wind reversals. The word monsoon comes from Arabic mawsam, season, referring to seasonal wind patterns bringing major precipitation shifts. Monsoons are large-scale wind reversals driven by temperature differences between land and sea. South Asian monsoon, most powerful monsoon on Earth, India, Bangladesh, Nepal. In summer, land heats faster than ocean, creating large, low-pressure areas over the Indian subcontinent. Moist air from the Indian Ocean rushes in, rises hitting the Himalayas, and condenses into vast rain columns. Result, weeks or months of nearly non-stop precipitation. Essential to life, watering crops, filling rivers, recharging aquifers, but also brings dangerous floods, landslides, and disruptions. Other regions, Thailand, Vietnam, Philippines, Northern Australia, also experience monsoons, though timing and strength vary. Desert weather, land of extremes, deserts are often thought of as empty, but they're teeming with atmospheric action. Sahara, world's largest hot desert. Daytime temperatures soar above 120 degrees Fahrenheit, while nighttime temps plummet 50. Massive swings due to dry air and lack of vegetation. Without moisture to hold heat, ground quickly radiates warmth back to space after sunset. Dust storms. Habub in North Africa/Middle East, towering walls of dust created when cold downdrafts from thunderstorms hit ground and push dry soil, sand into air. These walls stretch for miles, reduce visibility to zero, sweep across cities like giant erasers coating everything in grit. Similar phenomena in Australia, red dust across continent, and American Southwest late summer thunderstorm activity. Polar regions, ice, wind, and extreme light. Arctic and Antarctic weather, ruled by ice, wind, and extreme light cycles. Winters bring perpetual darkness and frigid temperatures. Summers bring endless daylight and melting permafrost. Katabatic winds, cold, dense air flowing downhill from ice-covered plateaus. In Antarctica, these reach hurricane force, sweeping snow across frozen landscape in blinding whiteouts. Despite cold, polar regions are technically deserts, receiving very little precipitation. Most snow fell thousands of years ago and never melted. Tropical rainforests, daily thunderstorms, tropical regions near equator, Amazon, Congo Basin, Southeast Asia are home to rainforests, receiving consistent heavy rainfall year-round. Convectional rainfall dominates. Intense solar heating during day causes warm air to rise rapidly, condensing into towering clouds by afternoon, producing near-daily thunderstorms, usually short but intense, releasing rain bursts nourishing biodiverse ecosystems. Farther from equator, savanna zones have seasonal rainfall, long dry periods followed by wet weather bursts, shaping ecosystems where grasses dominate. Island nations and ocean currents. Pacific island nations experience unique weather systems. Trade winds, tropical cyclones, ocean currents all play major roles. El Niño Southern Oscillation, ENSO, one of most influential global patterns. During El Niño, warm Pacific waters shift eastward, disrupting rainfall across South America, Australia, Southeast Asia, Africa. La Niña brings cooler waters, shifting patterns oppositely. Ocean currents, Gulf Stream and Atlantic, Kuroshio and Pacific, regulate climate by transporting warm water from tropics toward poles, influencing coastal temperatures and weather patterns, making places like UK much milder than other similar latitude areas. Mountainous regions, orographic effects in mountains, Andes, Himalayas, Rockies. Elevation plays key roles. As air rises over mountains, it cools and loses moisture, creating orographic precipitation on windward sides. On leeward sides, rain shadow. Air descends, warms, and dries out, leading to arid conditions. This is why places like Chile's Atacama Desert, west of Andes, are among Earth's driest. Coastal versus inland climates. Coastal areas. Ocean proximity moderates temperature, bringing milder winters and cooler summers. Inland, temperatures swing more dramatically season to season. Central Asia can experience blazing summer heat and brutal winter cold, while coastal Norway, thanks to Gulf Stream, enjoys relatively mild winters despite being far north. Microclimates. Even more variety comes from microclimates, shady ravines staying cool and moist, while nearby hills bake in sun. City blocks with glass skyscrapers reflecting enough heat to feel degrees warmer than nearby parks. Vineyards, on one slope producing different grapes than vineyards, just over ridge. Every region has its own weather signature shaped by unique combinations of latitude, terrain, ocean proximity, and atmospheric patterns. Yet despite variety, underlying principles are same. Heat rises, moisture condenses, air moves from high to low pressure. From driest deserts to wettest rainforests, rules are consistent, even if results are wildly different. Wherever you are, watching lightning dance across tropical skies, waiting out desert dust storms, or standing in still silent polar snow, you're experiencing one version of the same global story written in wind, water, sunlight, and shadow, woven through every corner of Earth. Weather forecasting, reading the sky. We've explored what weather is, but how do we know what's coming? How can we predict next storms or sunny days? Weather forecasting might seem like science mixed with guesswork, but it's actually a finely tuned art based on physics, data, and careful observation. Observing the present. To predict the future, meteorologists first need to know exactly what's happening now, not just in your town or country, but across the entire globe. Weather is interconnected. A Texas thunderstorm might be part of larger systems eventually influencing New York or Europe. Data collection tools, weather stations, ground level, dotted across the planet, recording temperature, humidity, wind speed, slapshy pressure, precipitation. Some automated, others human monitored. Every few minutes, they send data to central databases, painting real-time atmospheric pictures. Weather balloons, released from various points worldwide, usually twice daily. Each balloon carries small instrument sets, measuring conditions while rising to 20+ miles altitude before bursting. These measurements are crucial for understanding vertical atmospheric structure, how temperature, humidity, wind change with height. Vertical profiles help determine if atmosphere is stable, stormy, or in between. Satellites, the real revolution in forecasting, orbiting hundreds, thousands of miles above Earth, providing continuous images and data from space. Geostationary satellites stay in one position relative to Earth, providing constant coverage of same area. Polar orbiting satellites sweep pole to pole, gradually imaging entire planet. Satellites see clouds, measure sea surface temperatures, track hurricane formation, detect moisture levels, monitor volcanic ash, wildfires, snow cover. Many weather report images, colorful animations showing swirling clouds and approaching fronts, come from satellite data, radar, critical for short-term forecasts. While satellites provide bird's-eye views from space, radar looks horizontally across land. Weather radar sends radio wave pulses bouncing off precipitation. By measuring return signal strength and timing, radar determines where rain snow is falling, how heavy, and how fast it's moving. Doppler radar detects motion within storm systems, invaluable for identifying rotating thunderstorms potentially spawning tornadoes. Numerical weather models, all this data, billions of points daily, feeds into numerical weather models, computer programs simulating atmospheric behavior based on physics laws. They divide the world into giant 3D grids, each cell representing small atmospheric chunks. Within each cell, models calculate how temperature, pressure, moisture, wind will change over time based on surrounding conditions. Process is incredibly complex. Each model runs on powerful supercomputers, churning through equations representing atmospheric dynamics, thermodynamics, radiation, cloud formation, and more. Major weather models, GFS, Global Forecast System, US, ECMWS, European Center for Medium Range Weather Forecasts, UK Met Office, each has strengths, weaknesses, and focus areas. Uncertainty and chaos. Despite sophistication, forecasts involve uncertainty. The atmosphere is a chaotic system. Small initial condition differences lead to big outcome changes. This is the butterfly effect. A butterfly flapping wings in Brazil could theoretically set off a Texas tornado. It's a poetic way of saying even tiny measurement errors can grow into large discrepancies over time. To manage uncertainty, meteorologists use ensemble forecasting. Instead of running models once, they run dozens of times with slightly different starting conditions. Results produce ranges of possible outcomes, which can be average slightly scenarios. If all model runs agree, forecast is high confidence. If they diverge, situations are more unpredictable. Human expertise forecasts also rely heavily on human expertise. Meteorologists interpret model outputs, compare different models, consider local effects, and apply knowledge to refine computer suggestions. Models might not know peculiar ways certain mountain ranges funnel wind, or how particular coastlines generate fog. Human judgment still plays vital roles. Forecast accuracy. Accuracy has improved dramatically over past decades. Today's day forecasts are roughly as accurate as 1980's day forecasts. 5. Day forecasts are pretty reliable. Even 10-day forecasts, while less precise, give decent trend senses. Still, farther out you go, blurrier pictures become. Tiny uncertainties multiply. Exact timing/location becomes harder to pin down. Nowcasting and probabilistic forecasting, short-term forecasts, nowcasting, are especially useful for rapidly evolving events. Thunderstorms, tornadoes, these rely on high-resolution radar, local observations, and frequently updated models. Meteorologists use this data to issue watches and warnings, helping people stay safe during severe weather. Probabilistic forecasting, rather than saying it will rain tomorrow, forecasts might say there's 70% chance of rain tomorrow. This reflects forecasts' true nature, not guarantees but likelihoods based on current information. Probabilistic forecasts help people make better decisions, packing umbrellas, rescheduling picnics. Beyond tomorrow, forecasting plays huge roles in aviation, shipping, agriculture, emergency management. Airlines plan flight routes avoiding turbulence. Farmers depend on rainfall predictions for irrigation. Utility companies adjust systems based on expected heat/cold. Emergency responders prepare for hurricanes, floods, wildfires. Machine learning and AI weather forecasting is expanding into machine learning and artificial intelligence, being used to analyze vast data sets, spot subtle patterns, and improve model accuracy. While they won't replace traditional forecasting soon, they're becoming valuable tools. You're part of forecasting too with smartphones and apps. Millions now report local conditions through crowdsourcing platforms. These observations help fill gaps between official stations, providing more detailed ground-level snapshots. Next time you check forecasts seeing 72 degrees Fahrenheit with 20% chance of showers, remember what went into that little icon? Hundreds of satellites orbiting Earth, balloons floating miles above, supercomputers solving billions of equations. meteorologists interpreting complex data, and yes, maybe someone like you standing in backyards noticing sudden breeze changes. It's a staggering collaboration, a global effort to read the sky. While we can't control weather, our ability to understand and predict it has never been better. Climate change and evolving weather. Weather has always been a shapeshifter, sometimes gentle, sometimes fierce, always moving. But over the past century, especially recent decades, we've begun noticing something remarkable. Weather itself is changing. Not just day to day or season to season, but over time's long arc. At this transformation's heart is climate change. Weather versus climate weather is the atmosphere's mood, what it feels like today or tomorrow. Raining, hot, breezy. Weather is short-term and highly local. Climate is the atmosphere's personality, average of all those moods over long periods, typically 30+ years. Climate tells us what's typical for places, how much rain usually falls in spring, how cold winters tend to be, how often storms roll through. Climate has never been perfectly stable. Over Earth's history, it's swung from ice ages to warm interglacial periods driven by natural cycles. Earth's orbit shifts, volcanic activity, solar output. But what we're seeing today is different. Changes are happening faster, primarily driven by human activity. The warming trend since the late 19th century, average global temperature has risen more than 2 degrees Fahrenheit. That might not sound like much, but for a system as large and sensitive as Earth's climate, it's a big deal. This warming is largely due to the greenhouse effect, a natural process where certain gases trap heat in the atmosphere, keeping our planet warm enough to support life. Key greenhouse gases: carbon dioxide, methane, nitrous oxide, water vapor. Of these, carbon dioxide plays starring roles in today's climate story. Released when burning fossil fuels, coal, oil, natural gas, deforestation adds to the problem by reducing trees that absorb CO2. As greenhouse gas concentrations rise, more heat gets trapped. Result: warming planet. That warming doesn't just mean warmer summers, it means changes in weather patterns worldwide. More frequent, severe heat waves, prolonged intense heat periods, are becoming more frequent, severe, and long-lasting. In many regions, heat waves that used to occur once every 20 years now happen every few years or annually. Urban heat islands amplify effects, making cities particularly vulnerable. Nights are warming faster than days, seemingly small detail with big implications. Warmer nights offer less relief from daytime heat, increasing stress on human bodies and reducing chances for crops and animals to cool down. Shifting precipitation patterns. Some areas get wetter while others dry out. Warmer air holds more moisture, about 4% more per 1 degree Fahrenheit increase. That means when it rains, it often rains harder. We're seeing more extreme rainfall events with intense downpours, overwhelming drainage systems, flooding streets, washing away soil. But more moisture doesn't guarantee more rain everywhere. Some regions are becoming drier, especially those already drought-prone. Longer dry spells combined with higher temperatures lead to parched soils, shrinking rivers, stressed ecosystems. In southwestern US, southern Europe, and parts of Africa, droughts are becoming more frequent and severe. This pattern, more extremes in both directions, is a hallmark of climate change. Wet areas get wetter, dry areas get drier. Changing storms, warmer ocean temperatures provide more energy for tropical storms, potentially leading to stronger hurricanes, cyclones, typhoons. Evidence shows while total annual storm numbers haven't increased dramatically, storm intensity has. We're seeing more Category 4, 5 hurricanes capable of catastrophic damage. These storms also hold more moisture, meaning more rainfall at landfall. Hurricanes like Harvey, 2017, and Florence, 2018, dumped astonishing rain amounts, causing widespread flooding far from coasts. Winter storms are also affected. Warmer atmosphere doesn't mean no snow. In fact, it can mean more snow in some places because air carries more moisture. But timing and nature of winter weather are changing. Snow seasons start later and earlier. Snowpack, natural mountain water storage, is shrinking. Jet stream changes, climate change is altering the jet stream, the high altitude wind river helping guide weather systems across the globe. As Arctic warms faster than the rest of the planet, Arctic amplification, temperature differences between poles and equator weaken. This can slow down and cause jet streams to wobble, leading to unusual weather patterns. Slower, wavier jet streams can cause weather systems to stall. Rainstorms lingering over same regions for days or heat waves locking in place. These stalled systems have been linked to several recent extreme events. Sea level rise, not weather itself, but having profound effects on how weather is experienced, especially in coastal areas. As glaciers melt and oceans warm and expand, sea levels are rising about 8 inches since late 1800s. Higher sea levels mean storm surges and tidal flooding are more destructive, reaching farther inland, affecting more people. Wildfires, climate change influences wildfires not directly through flames/smoke. Hotter temperatures, drier soils, earlier snowmelt create longer fire seasons. Lightning strikes, natural ignition sources, may increase with more convective storms. Once fires begin, high winds and dry vegetation allow rapid spread. Result: more intense, frequent, damaging wildfires worldwide. Attribution science. These changes don't mean every weather event is now caused by climate change. Weather will always be variable. There will always be cold snaps, rainy days, mild seasons. But scientists can now study how climate change increases likelihood or intensity of specific events through attribution science, helping us understand how warming world background conditions shape what the atmosphere delivers. What can be done? Not all change is inevitable. While some warming is already baked in due to past emissions, future outcomes depend on choices we make today. Reducing greenhouse gas emissions, switching to renewable energy sources, improving energy efficiency, protecting forests, changing how we grow food and use land. Adaptation is also key. Communities redesigning infrastructure for heavier rains, planting trees to cool cities, updating building codes for stronger storms. Farmers experimenting with drought-resistant crops, cities mapping flood zones and building seawalls, individuals learning to stay safe during extreme heat, conserve water, reduce carbon footprints. Even small actions matter. When multiplied across millions of people, actions become powerful. Walking instead of driving, turning off unused lights, supporting environmental protection policies. These add up like raindrops in storms. The weather is still weather, capricious, beautiful, unpredictable in details. But the canvas it paints on is changing. Boundaries have shifted, stakes have risen, and we are both observers and participants in that change. Next time the sky darkens unexpectedly, summer feels a bit too long, or rains come harder than usual, remember you're witnessing not just weather, but a chapter in the larger story of a planet in transition. A story still being written by wind, water, people, and still very much within our power to shape. And so we've drifted through winds and rains, floated with clouds, and stood in the quiet hush of falling snow. We've explored lightning-lit skies, watched deserts shimmer in silence, and traced invisible hands guiding weather from one side of the world to the other. From gentle fog to towering hurricanes, from sunlight science to wind's whispers, we've uncovered just a little of how this beautiful, chaotic, ever-moving system works. Weather is more than background noise. It's a conversation between earth, ocean, and sky. A language of temperature, moisture, and motion written in clouds and spoken in thunder. It shapes landscapes we live in and lives we lead. It brings harvests and hardships, calm mornings and wild afternoons. And despite all our instruments, satellites, and models, it still finds ways to surprise us. As you close your eyes tonight, tucked in wherever you are, the atmosphere keeps moving. Wind flows silently over mountaintops. Raindrops gather on leaves. Somewhere far away, a snowflake is beginning to form. It's comforting to know the sky never truly sleeps. It simply shifts, reshapes, and continues its slow dance above us. Thank you for being here, for winding down with me and joining this journey through the science of weather. If you found this calming, curious, or just a little bit magical, please consider leaving a like or subscribing to The Sleepy Scientist. It helps others find their way here too. Now rest well. Let your thoughts drift like clouds, and may your dreams be as soft as fog and as bright as morning after rain.